The idea behind photo or sonophonodynamic therapy has been around for a while. You'll find about 4,000 scientific reviews. You'll find a couple hundred university studies working on this technology as we speak. I think the problem that we tend to see with the conventional model or the conventional versions of this therapy is the toxicity of the agents that they're using. The light is essentially used to excite chemo agents, and as you know, chemo lacks targeting capabilities, and so what you're left with is this generalized toxic impact. So conventional wisdom has once again taken a good idea and kind of ruined it. Over the last couple of decades, the Russians and several of the Baltic states have employed the use of algae or other chlorophyll agents in place of toxic agents. The problem there is that the chlorophyll agents, in their non-toxic state, they really just don't adhere to cancer cells very well. And when they do adhere, their response to light activation produces minimal oxygen radicals that have low oxidative reduction potential, meaning that they just don't burn very hot. These compounds produce singlet oxygen in the wrong part of the cell. That's another problem. They rely on the presence of molecular oxygen to form their effect. That's another problem. Remember, cancer cells, they don't have a lot of oxygen. And the non-toxic chlorophyll agents tend to degrade in the system. In other words, they're not stable. And once they degrade, they're not going to produce any singlet oxygen. So again, you now have the integrative world using photodynamic therapies or sound-activated therapies or maybe a combination of both in a manner that generates minimal response at a cancer cell. Yes, you have no toxicity, but you also have very little effect. We've taken a different non-toxic approach, but one that has much greater effectiveness, using what we call M-state elements that are bound with singlet oxygen. Of necessity, you have to solve the existing problems. So what I'd like to do is just take a look at each of these problems and quickly explain how we've attempted to solve the issue. Number one, site adhesion. You have to get the agent to adhere to the cell structure, expose it to the light to generate the free radical to kill the cell. The issue with the natural versions of chlorophyll is that they'll accumulate in the cell, but they won't adhere to the structures that need to be targeted. Our approach is something that we call pathway-specific accumulation. In this case, we want to accumulate something in several pathways in the complex 1 protein of the mitochondria, and a specific effect that we want is a change in the signaling patterns that control growth. In normal cells, we just get an improvement in energy production, kind of cleans out the membrane. So again, some collateral benefits to the normal cells and applicable to probably many pathologies or general health. Zero side effects, but with specific targeting capability. Number two, singlet oxygen production. Again, with the natural chlorophyll agents, you're just not going to get a lot of singlet oxygen production. Out of the M-state oxides, they generate about 50 times the singlet oxygen that is compressed into the pathway that we want to affect specifically. We're not just spreading the thing throughout the entire cell, specific pathway. Number three, ORP values. As I pointed out, the activity rate, how hot the oxygen burns, is much too low with the chlorophyll approach. The ORP values that we get out of the oxygen released from the M-state materials is about 3 to 5 times that provided through the chlorophyll agents.